Welcome to lesson 1.6, classify polygons. So in this lesson, obviously our main idea is going to be looking at polygons and how we classify, define, describe different polygons. So the first thing we have to start with is our geometric definition of a polygon. So the first part of our definition, it's a closed plane figure meaning it lies in a singular plane, with the following properties. And to be closed means that there's no opening within the figure. So for example, if B to C did not connect with C and D, that would be an open figure. So it's a closed plane figure with these two following properties. Property 1, it is formed by 3 or more line segments called sides. So pretty standard there, formed by 3 or more line segments called sides. Now part 2 is the more specific, and the part where, if you don't pay close attention, you may miss part of the definition. So it's a closed plane figure, 3 or more line segments called sides, and each side intersects exactly 2 sides, one at each endpoint. So side BC, for example, intersects side CD and BA at the endpoints. And then no 2 sides with a common endpoint are collinear, meaning they're not the same side or they don't lie on top of each other. So the way we can name a polygon is by listing the vertices in consecutive order. So we'll use this pentagon here, and we could start, for example, in alphabetical order and go around A, B, C, D, E. I could start at D and name this polygon D, E, A, B, C. I could start at C and go the other way and call it polygon C, B, A, E, D. As long as you're going in order around the perimeter with the vertices, that's an acceptable way to name it. So a vertice is the plural of vertex. And a vertex is the end point of each side. So B would be a vertex, C would be a vertex, D, and so on. My apologies for the random coordinate plane here. Just ignore that. That should not be there. Then we have 2 types of polygons. We have a convex polygon and a concave polygon. So a convex polygon, no line that contains a side of the polygon also contains a point in the interior of that polygon. So what they mean by that, if we look at this first one here, if I would extend any of my sides forever, making them a line, so this one here would extend forever, here forever, here forever, here forever. If none of those sides cut through the interior, then it is a convex polygon. A concave polygon is any polygon that's not convex. So any polygon where if we extend the sides forever, making them lines, if one of those lines cuts through the inside of our polygon or the interior, then it is concave. So if we look at our second example here, this little side, when we extend it into a line, it cuts through the interior right here. So that would be a concave polygon. So example 1 asks us to tell if the figures are polygons and whether they're convex or concave. So in A, this figure would not be a polygon because some of the segments intersect more than 2 different segments. Also, we have this segment in the middle. So this segment in the middle is our problem segment because this one segment intersects 1, 2, 3, 4 different segments. And again, a side can only intersect 2 segments. In B, each side intersects 2 other sides at the endpoints. It's a closed figure. All the sides are straight segments. So yes, it's a polygon, and it would be convex because if I extend any of these sides forever, not a single one would cut through the interior. In C, I notice we have a curve as part of our perimeter. That cannot happen with a polygon. We need straight line segments. So no, this is not a polygon. Part of the figure is a curve, not a segment. And then in D, all the sides are line segments. They all meet at their endpoints and intersect 2 other sides. So yes, it is a polygon, but this one is concave because if I would extend, for example, this little vertical side here, it would cut through the interior right here. So if any of the sides extended cut through the interior, it is concave. Then we have this 2-part table for classifying polygons. And again, classifying is simply the process of naming based on properties. So the way we name polygons or classify them is based on their number of sides. Obviously, certain polygons have special names, like 3 sides are triangles, 4 sides are quadrilaterals. Anything with 5 sides is a pentagon, 6 is a hexagon, 7 is a heptagon, 8 octagon, 9 nonagon, 10 decagon, 12 dodecagon, and then we have n, meaning for any number of sides, if we don't have a special name like triangle, quadrilateral, pentagon, we can simply name a polygon based on its number of sides. So an n-gon is where n is the number of sides. So for example, a 14-sided polygon simply can be called a 14-gon. A 21-sided polygon can be called a 21-gon. So the number of sides, hyphen gon. Then 2 special types of polygons. An equilateral polygon is a polygon where all the sides are congruent, meaning they're all the same length. An equiangular polygon are where all the angles in the interior of the polygon are congruent. So that would be looking at each one of these angles. So here, 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 and here. If those are all congruent, then it is equiangular. If a polygon is convex and both equilateral and equiangular, it is known as a regular polygon. So a regular polygon first is convex, then we know all the sides are congruent and all the interior angles are congruent. So example 2 asks us to classify the polygon by the number of sides, then tell whether it is equilateral, equiangular, or regular. Explain your reasoning. So in part A, these little arcs on the angles, single arc means it's congruent to any other single arc. So all my interior angles have the single arcs, so they're all congruent. So I know it's equiangular. The little single hash mark on each side tells me each side with 1 hash mark are congruent. So it's also equilateral. Then I have to look at the sides to decide if it's concave or convex. All the sides, when extended, do not go through the interior, so this would also be convex. So if it's convex, equilateral, and equiangular, it is a regular polygon. It has 6 sides, so it's a hexagon that's regular. So if we were going to write that properly, we would call it a regular hexagon. In B, we have a 4-sided figure. Now, side 2 and 4 in this case would be congruent because they have the single hash marks. 1 and 3 have double hashes, meaning they're congruent to each other, but the double hash and the single hash mean these two are different. So we do not have 4 congruent sides. Same with the angles. The single arcs, these two are congruent. The double arcs, these two are congruent, but not all 4 are congruent to each other, so it is not equiangular. Now, when we look at it, 4 sides makes it a quadrilateral, but we do know it is convex if we wanted to add that label, but they're just asking equilateral, equiangular, or regular. If it's not equilateral and not equiangular, it can't be regular. And then in C, we have a 12-sided figure, so right away I know it's a dodecagon. Then all the sides have the single hash mark, meaning all the sides are congruent. Not all my interior angles have the same marking though. There's some here that are different than the right angles here. So it's not equiangular. So in this case, it's just an equilateral dodecagon. And originally, because it's also not convex, we don't even need to check if it could be regular. Part 3 is asking us to simply sketch examples of the following figures. So a convex heptagon, 7 sides, and no side when extended could cut through the interior. Doesn't matter if the angles and sides are the same, as long as it's convex with 7 sides. So here would be one example. A concave hexagon is 6 sides, and at least one of the sides, when extended, would have to go through the interior. So in this case, here's one example of a concave hexagon. 6 sides, and any of these extended would cut through the interior. And then in C, it says a regular pentagon. So I know I need 5 sides, and I need congruent sides and angles. So the way that I drew that, to be honest, I used a template. You just need to put in your hash marks and angles. You don't need to worry about drawing it perfect as long as you put the hash marks on each side, showing that they're congruent, and you put the arcs on each angle, showing that they are congruent. So we have 5 congruent sides, 5 congruent angles, so it's a regular pentagon. Now, example 4 is using this property and these different definitions to look at a word problem and do it algebraically to figure out the scenario's answer. So when we look at this scenario, first it tells us the table is shaped like a regular hexagon. So the fact that they tell me it's regular means all the sides are equal and all the angles are equal. So the expression shown represent the side lengths of the table. They want us to find the length of a side. So again, because it's regular, I know all my sides are equal. They gave me 2 sides. One is 3x plus 6, and one is 4x minus 2. I can set those 2 sides equal to each other to solve for x. So then to solve for x, 3x plus 6 equals 4x minus 2. subtract 3x from each side, and 6 equals x minus 2. Add 2, and 8 equals x. But they want to know how long a side is, not what's the measurement of x. So we take this x, and we could substitute it in to either of these expressions. So I substituted it into the top one, 3 times x plus 6. 3 times 8 plus 6 is 24 plus 6, which tells me each side is 30 inches. And then in part B, it tells us the expressions 8y and 9y minus 15 represent the measure of two angles in the table. Find the measure of an angle. So again, because it's regular, we know all the angles are equal. So we can set our two expressions equal to solve for y. So 8y equals 9y minus 15. Solve for y, so we could subtract the 9y from each side, and we have a negative 1y equals negative 15. Divide both sides by a negative 1, and y equals 15. Then we substitute the 15 in for y in either of those expressions. So I chose the 8 times y, so 8 times 15 tells me each interior angle is 120 degrees. So as you work through today's lesson, it all comes back to the definitions and their properties. So you want to make sure you understand this definition and properties of a polygon. And then you want to make sure also you know the difference between convex and concave. And finally, how to classify polygons and what equilateral, equiangular, and regular mean.